Welcome back to ECE 501B. Announcements are critical for the people that are on campus. The next time that we were scheduled to be here, don't show up. I won't be here. I will be somewhere else. And so for that reason, I'm going to try to do this virtually for you this time. We do have others that are online, then this will be no different from what they do, other than I don't have an audience to deliver to. And so it may get a little bit more dry if I'm sitting at a table trying to record this, but we'll see how that goes. But look for the upcoming material following today's material on D2L. That's where it will be housed. Homework 7 is due on the 23rd. That's, I believe, the Monday evening prior to the Thanksgiving break. And then the 7th is the last week, short week, is when homework number 8 is due. That's due then on a Monday. And I looked at the number of submissions for deliverable number 1, and that looked about right. I haven't verified that everybody's name is associated with a project, but that was due last night. I don't think I closed the Dropbox. I just had a due date. So if you haven't yet submitted deliverable 1, please do that as soon as possible. Deliverable 2, which is the main report for your project, and deliverable 3 is the reflective paragraph. Those are both due on the 9th, which, if my days are right, that's a Wednesday. What I do need you to be aware of is the final exam is on a Tuesday. So you may be plugged into a Monday-Wednesday sequence in this class. Hopefully you can think about linear algebra on a Tuesday. The final exam will be on a Tuesday, and it's starting later than what you normally have in this class, and it will be a 2-hour exam instead of a 75-minute exam.
What about the syllabus?
Pardon?
What about the syllabus?
What about the syllabus?
Yeah, will it be after exam 2 or whole portion?
Oh, you mean what will the topics be? It's going to be comprehensive. So the final exam will be comprehensive. It will cover material uniformly throughout the semester. So what we've covered since exam 2 will be on the final, but exam 1 and exam 2 material will also be on the final. And I'm hoping that it's somewhat uniform, but I could ask you a question from the last day of class, and it could be comprehensive, meaning everything sort of builds on itself in this class, and I could give you one problem that talks about the very last subject that we deal with on the last day of class, and that could cover the entire semester of material. But it will be more like exams 1 and 2. It will just be distributing that content across the entire semester. That's the final exam, the way I see it, and I will try to post some exam, maybe a review session for the exam, but probably not a practice exam for the final. Okay? So, you now have grown up. Now you have to have matured to that level for the final exam. Today what we want to do is review what we just finished, which was the complex spectral theorem, and then we need a little bit more background to jump into the real spectral theorem. As typically happens, the complex material is maybe easier or more straightforward to present or show than the real, or dealing with real vector spaces, and that's what we're finding here. So we have to give a little bit more background, which is the Cauchy-Schwarz, basically that inequality. We'll look a little bit about some algebra techniques that you've maybe used many, many years ago, completing the square. We will use that in this operator note, or in this operating domain, and then we will present lemmas 711 and 712 before we get into the real spectral theorem, which is result 13, and those numbers are all consistent with the second edition of the book. We'll then summarize those spectral theorems, the complex and the real spectral theorems. Then we will get into some later pieces in Chapter 7, positive operators. What do we mean by a positive operator? And there you might think of scaling. And if you think of these concepts like a complex number, the complex number has a in the, let's say, polar form, you have a magnitude and an angle. Now we want to think about these operators as having some magnitude, some scaling, and maybe some direction. And that's where the positive and the isometries come into play. The isometries gives us a direction associated with these operators, and the positive operator gives us a scaling. So if you wanted to think about it, you could say, okay, where are we turning, or in what direction are we moving with this operator, and how are we expanding or contracting? How are we scaling in that direction? That's how to start thinking maybe about these ideas, and a part of that in between will be what's a square root of an operator. You can take a square root of a number, a non-negative number, but now what's it mean to take the square root, or what is a square root of an operator? Let's bring ourselves back to where we have come from. And one in this particular chapter has been the adjoint, and that's really what do we have to do with this linear map to slide it from one slot to the other. That's how we've defined the adjoint. If we talk now about a normal linear operator, we're really meaning that that operator and its adjoint commute, and we could write it as t dagger equal t dagger t, or we could define it, a normal operator, in terms of norms. The norm of this operator applied to a vector is the same as the adjoint of that operator applied to the same vector. That's another way of defining a normal operator. And a self-adjoint operator just means that that linear operator is equal to its adjoint. Those are some three really quick definitions. Then with that background, we were able to develop the complex spectral theorem, and really this is, what does it mean, or what do we need from this operator in order to essentially be able to have a matrix representation that's diagonal? And what we need when we're dealing with this operator in a complex inner product space, we need that operator to be normal. That's all we need. And then if that's the case, then we can find an orthonormal basis consisting of eigenvectors of that linear operator. Meaning, the complex spectral theorem says, suppose we have a vector space that's a complex inner product space, and we have a linear operator t on that vector space. Then that vector space has an orthonormal basis consisting of eigenvectors of that linear map, if and only if that linear map is normal. Again, what does it mean to be normal? Well, you can think of it a couple of different ways. T and its adjoint commute. That's this equality relationship, or these norms are equal. The norm of the operator with a vector, that norm, or the norm of this operator's adjoint applied to that same vector. Those two norms are equivalent. If that's the case, then that particular linear operator is normal, and if it's normal on a complex inner product space, then the matrix representation of that linear operator can be diagonalized, and diagonal matrices are nice because now we can essentially think of in Nevada little problems sort of independently. We don't have to worry about how they are coupled as much, and we can think about what's happening with this diagonal matrix versus this generic or general linear map. That's one of the powers of this diagonal matrix representation. That's the review. Now, what we want to do before we can do something similar, and what we're wanting to do that we just did or showed in the complex inner product space, we were able to show that that operator was diagonalizable, or it had a matrix that had a diagonal representation. We would like to know what's required of this linear map T if we are working on real inner product spaces. What do we need to, or how do we need to constrain that linear map to maybe have a diagonal matrix representation of that linear map? To get there, let's just remind ourselves of the Cauchy-Schwarz inequality, and then we'll look at completing the square in the context that we need it, and then we will present lemmas 11 and 12 in Chapter 7 before we get to the real spectral theorem. Cauchy-Schwarz. That just says that the absolute value of this scalar, and the scalar is determined by taking the inner product of two vectors in a vector space, u and v, that's bounded above by the norm of those two vectors, the product of the norm of those two vectors. And if we remember another way of thinking about this absolute value, then I don't really need that absolute value symbol here. Now this inner product is bounded below by the negative of the product of the norms of u and v, and it's bounded above by the product of the norms u and v. We are actually going to use this lower bound on that inner product in our result that's forthcoming. That's what we need from the Cauchy-Schwarz, is can we bound this inner product of u with v? And we are going to actually be bounding it from below with that negative of the product of the norm of u with the norm of v. Let's now talk about completing the square. Now we will get down and start writing and not scrolling. Suppose we have the following expression. Where the following expression is x squared minus alpha xy plus beta y squared. And alpha and beta are numbers, real numbers. And the concept that we're going to be playing with is completing the square, which is really how do we create these first two terms in that expression. Meaning, if I wanted to create x squared minus alpha xy as a piece of something, some term that's squared or some expression that's squared, I could do that if I took x minus alpha over 2 times y and squared that. I would at least get those first two terms. Meaning, if I now square that expression, I end up with x squared minus 2 times x times the second term in that expression, which I'm going to sort of shuffle those around. Then I have plus the alpha over 2 squared y squared. That shouldn't surprise anybody. You learned that in your first algebra class, let's say. And if we simply simplify that middle term, we end up with x squared minus alpha xy plus alpha over 2 squared y squared. And what we're trying to do is key in on that piece, which is the same as that piece. So what we want to do is really rewrite this term or this expression in blue as a combination of two pieces. And one of those pieces is going to be that left-hand expression that's squared in black. Meaning, let's now start with x squared minus alpha xy plus beta y squared. We can now say that that's equal to x squared minus alpha xy. And if I now add in 0, I can make 0 out of just a combination of two terms. I can add a term and I can subtract a term. So that that piece is still 0. And I now have a plus beta squared y squared. Meaning I've really just rewritten that blue expression. I've just added 0 to it. But if I now combine that using the expression above in the note and collecting the first three terms, I can write those as x minus alpha over 2y squared. And then I have a plus, let's say, whoops, why did I square that beta? You guys need to wake me up. So that's beta times y squared, isn't it? That's what it was in blue. That's now what it is in black, so that I now can say that I have plus beta minus alpha over 2 squared times y squared. Have I made any mistakes? So that now I can be assured that that blue expression on the left will be positive as long as what? The first term on the right is non-negative because it's squared. The term on the left or on the right, or the second term on the right, so this piece here is non-negative. This piece will be non-negative under what conditions? As long as that expression is bigger than 0, right? Because I have the y squared, that's non-negative. So I need now beta minus alpha over 2 squared to be, let's just use a strict equality. Let's say that's greater than 0, because that's what we're going to use in our result later. And I can now say, well, that's now beta minus alpha squared over 4 greater than 0. Or if I add alpha squared over 4 to both sides, I have beta is greater than alpha squared over 4. Or what we might write this as, if I scale both sides by 4, alpha squared needs to be less than 4 beta. And that's how we're going to express our relationship between alpha and beta in the next lemma. But if we can assure ourselves that alpha squared is less than 4 beta, then this particular expression is going to be non-negative, the blue expression. And that we obtain by just completing the square. Now we're ready to state lemma 11 from chapter 7. Suppose we have a linear operator t on a vector space V, and let's make that linear operator self-adjoint. That just means it's equal to its adjoint. If we have two scalars, alpha and beta, that are real, such that alpha squared is less than 4 beta, then we are going to be able to conclude that this new operator, that's a combination of 3 operators, t squared plus alpha t plus beta I, that operator is in fact invertible. That's lemma 711. We have a linear operator that's self-adjoint, that's t. If we combine that in the way of t squared plus alpha t plus beta I and form a new operator, when alpha and beta are such that alpha squared is less than 4 beta, then that linear operator is invertible. So let's see if we can show that. And if you want to go back to your high school days, you can be thinking about the quadratic formula, and that's where this alpha squared and 4 beta are really coming from. It's really, when do you end up with imaginary roots? We're sort of forcing that to be the case with this discriminant where you're looking at this radical that's, let's say, if you had ax squared plus bx plus c and you were finding the roots of that, then the square root of b squared minus 4ac, you need that to be negative. Well, that's what we're sort of assuming here. Now, assume that we have these real variables, alpha and beta, such that alpha squared is less than 4 beta, and V is a non-zero vector in our vector space capital V. Now let's just write down an inner product where the inner product is a linear map, t squared, which I think you can guess what this linear map is going to be structurally. It's t squared plus alpha t plus beta I, and that's applied to this non-zero vector v, and we are going to form the inner product of that linear operator applied to v to v. And now we have all of these tools available to us in terms of how we can manipulate this inner product. First, let's distribute those operators into multiple different inner products by linearity of the first slot. which means that we are going to now write that leftmost inner product as the inner product of t squared v with v, and factoring out the alpha, since that's in the first slot and it slides right out of the inner product, alpha scaling the inner product of tv with v, and similarly we can factor out that beta from the inner product of v with itself. That should be straightforward. That's just a direct application of linearity of the first slot. Now what we want to do is actually break that t squared up and put half of it essentially into the second slot. So we're now rewriting t squared as t operating on tv, and then we want to take that first t into the second slot. Or we are now going to use the definition of the adjoint to rewrite that first inner product expression as tv inner product with t dagger v. Is it clear where that came from? We're just writing t squared as tt and moving the first t into the second slot, and that means we need to take its adjoint. And we'll just write down the second, or the next two inner product expressions. But we assumed that t was self-adjoint. So t dagger is equal to t, and that allows us now to rewrite that first inner product as tv inner product with itself plus alpha tvv plus beta vv. The first and third terms in that chain of inner products, we can just use the definition of the norm to rewrite those, so that the first term is now the norm of tv squared plus alpha scaling the inner product of tv with v plus beta times the norm of v squared. And now is sort of the key step in all of this. Now what we want to do is lower bound that rightmost expression using the Cauchy-Schwarz. And we only have one inner product in there, so now we can say, let's create this lower bound on this rightmost expression. Using the Cauchy-Schwarz inequality, so that we now have that's greater than or equal to the norm of tv squared minus alpha times the norm of tv times the norm of v plus beta v squared. And this should look similar to what we had before. Now we just have a number, because the norm is just going to be a scalar, and we're going to square that. So we have x squared minus alpha xy plus beta y squared, essentially. Now we can use our completing the square relationship that we developed before. Meaning now, keeping that inequality, we have the norm of TV minus, let's now take the absolute value of alpha over 2 times the norm of V squared minus, what have we really added in? We've added in alpha squared over 4 times the norm of V squared, so we're going to have to remove that, plus beta times V squared. And that's what we did with completing the square before. Or now we can write that as this first term is the norm of TV minus the absolute value of alpha over 2 V squared plus beta minus alpha squared over 4 times the norm of V squared. And we are actually wanting this piece, this scalar, to be positive. And we can assure that by saying that beta minus alpha over 4 squared is greater than 0, or beta is greater than alpha squared over 4, or now we can multiply through by 4 and just rearrange that and say we now have alpha squared is less than 4 beta. And if that's the case, then now that entire right-hand side is going to be greater than 0. As long as alpha squared is less than 4 beta, then if we assume that that's strictly positive, then, and we assume that V was non-zero, so we know the norm of V squared is something that's positive. As long as alpha squared is less than 4 beta, then we know that that entire left hand that we started with here is positive. So what does that say? Well, let me just rephrase that, or say that what we've just shown is the inner product of t squared plus alpha t plus beta I times V, inner product with V is now greater than 0. That's what all of this development has allowed us to conclude. That leftmost expression is now greater than 0 as long as alpha squared is less than 4 beta. But if this expression is greater than 0 for a non-zero vector V, what does that mean in terms of, let's say, what's happening in the first slot? If we know that that inner product is strictly positive and V is a non-zero vector, can we say anything about V and how it, let's say, is related to that operator, t squared plus alpha t plus beta I? If we just had some operator m applied to V, then we need to make sure that V is what? Not in the null space of that operator. If it was, then that operation would give us the 0 vector, And the 0 vector times any vector v, or inner product with any vector v, will give us something that's not positive. It will give us 0. So this expression is basically saying that that piece in the first slot has to be non-zero. If that first slot vector is non-zero, that means that v cannot be in the null space of t squared plus alpha t plus beta I, that operator. That's what I'm trying to say therefore. Therefore, v, this vector, this non-zero vector, cannot be in the null space of t squared plus alpha t plus beta I. And v, remember, was an arbitrary vector. And if v is an arbitrary vector, and no matter what the v is, as long as it's non-zero and it doesn't live in the null space of that operator, what's that tell us about that operator? It's injective, isn't it? So now we know that t squared plus alpha t plus beta I has a trivial null space, or it's injective. And that operator is, well, it is an operator, it's square, and we had that earlier result that related injectivity, surjectivity, and invertibility, and they were all three equivalent. So now that we have shown that that operator is injective, that now implies that t squared plus alpha t plus beta I is invertible. And if you remember, that's what we were trying to show. We were trying to show that as long as t was self-adjoint and alpha squared was less than 4 beta, then this particular operator, t squared plus alpha t plus beta I, was in fact invertible. We're going to need that. What else are we going to need? We're going to need Lemma 712. Lemma 712 says the following: if t is a linear operator and it's self-adjoint, then that operator t has an eigenvalue. So now I'm going to refer that proof to the textbook, but now we have this self-adjoint map from 711 and 712, those two lemmas, and now we're ready to start or to state the real spectral theorem. Which says the following: suppose that this vector space V is a real inner product space and T is a linear operator on that real inner product space. If that's the case, then V has an orthonormal basis of eigenvectors of T if and only if T is self-adjoint. So now, instead of when we were dealing with a complex inner product space, we needed the linear operator to be normal. Now if we're dealing with, to find this basis that was orthonormal with the basis vectors being eigenvectors, now when we're dealing with a real inner product space, we need this linear operator to actually be self-adjoint. Again, I'll refer you to the textbook for that, and let's just remind ourselves of what we now have relative to diagonal matrices. If we have a normal operator, or normal operators have diagonal matrix representations, on a complex inner product space, and self-adjoint operators have diagonal matrix representations on real inner product spaces. So if we want to have a diagonal matrix, then it's going to be possible on either a real inner product space or a complex inner product space if we put some constraints on those linear operators. In the real inner product space, we need the operator to be self-adjoint, and in the complex inner product space, it only needs to be normal. And we can sort of summarize that then as follows. A vector space V has orthonormal basis of eigenvectors of a linear map T, linear operator, if and only if A, V is a complex inner product space and T is normal, or B, V is a real inner product space and T is self-adjoint. So now we have conditions on these linear operators on either complex inner product space or a real inner product space for us to have a matrix representation associated with those linear operators that are diagonal. And the conditions are if T is normal on the complex inner product space, or if T is self-adjoint on a real inner product space, then we can get this orthonormal basis of eigenvectors. Now, what we may not always be able to do is have these nice diagonalized matrix representations, and we may need to start generalizing some of these concepts. And to do that, let's now talk about positive operators, and which are dealing with scaling, and then we'll talk about isometries, which are these directions. So let's now talk about positive operators. Which in the second edition is on page 144. And when we think about positive operators, you might start thinking about scaling, either contraction or expansion. Here's a definition. An operator T that's a linear operator is positive if two conditions are satisfied. First, T needs to be self-adjoint, which that just means that T is equal to its adjoint, and we want the inner product of TV with V to be non-negative for all vectors on our vector space capital V. So that's what, when we talk about a positive operator, that's what we are going to mean, that it has these two conditions. One, it's self-adjoint, and if we take that linear operator and use it to operate on an arbitrary vector V and inner product that vector with V itself, it's going to be non-negative. That's what we mean by a positive operator. Now, one sort of specialization on that is if our vector space, and in this result for the positive operator, we didn't say what V was, whether it was a complex vector space or a real vector space. If V is complex, or we now have this complex vector space V, then T, this linear operator, is self-adjoint when the inner product of TV with V produces a real number. That's an earlier result, but let's now see if we can sort of convince ourselves of why that's true. Let's now look at sort of an explanation, or what I'll call a justification of this note. What do we know about the inner product, and if we interchange the vectors in the slots? What did we call that? Or Was there some kind of symmetry? It was conjugate symmetry, wasn't it? So the inner product is conjugate symmetric. Which really just says that if we looked at the inner product of TV with V, if we now interchange the vectors in the slots and said, oh, V, TV, that inner product is actually the complex conjugate, or the complex conjugate of that inner product is equal to what's on the left-hand side. That's the conjugate symmetry of the inner product. Now, what we want to look at, though, is what happens if this inner product of TV with V, when that's real. Let's show that that actually implies that this linear map T on a complex inner product space is actually self-adjoint. So let's assume that the inner product TV and V is real. If the inner product of TV with V is real, that says that the conjugate of that real number is equal to itself. Meaning if we took the conjugate of the inner product of TV and V, which is just that, so that's an overbar, that's not an underline of what's above, that's equal to, if the inner product of TV and V, if we conjugate it, it's equal to the inner product. Are we okay with that? Pardon? So the overbar, I'm taking the complex conjugate of the scalar that results from the inner product of TV with V. That's what I'm meaning by that huge bar. I'm taking the complex conjugate of the scalar that results from TV with V's inner product. And if the inner product of TV with V is real, then that's equal to the complex conjugate of that scalar. But suppose that I now take the complex conjugate of TV with V. And now what I want to do is apply conjugate symmetry to what is the inner product. Meaning, if I now said, how do I want to say this? Let me not do that just yet. I now know that the inner product of TV with V by conjugate symmetry is V TV inner product. Is that correct? But now let me take the complex conjugate of both sides. That should still be equal. But what happens when I take the complex conjugate of the complex conjugate? I get the same thing, or what I started with back, which is just V TV. And I hope what you've seen, or what you can see then, that here is this and that. Those are the exact same expressions. So that whatever those are equal to must be equal. And so now I'm hoping that you see that the first line must equal the second line. So the blue highlights now say, therefore, the inner product of TV with V from the blue highlights must equal the inner product of V with TV, and that's because that first inner product we assumed was real. Now, what we can do is we can start playing a little bit with the adjoint expression, or how to find the adjoint. So we know that these two inner products are equal. And since TV with V is equal to, if we now used the adjoint expression, what would this be equal to? Or if we now said inner product of TV with V and we want to push that T to the second slot, what would be on the right-hand side of that equality? It would be V T dagger V. And that's by the definition of the adjoint. But now if we look at what's in the second slot of those equal relationships, which I've underlined with this blue highlight, now we can say that T dagger is equal to T, or in fact that as if we start with the inner product of TV with V being real, then we can conclude that that linear operator T is self-adjoint. And that's what we concluded at the end from that development, or that's the justification of that note. Now let's just look at some examples of positive operators. Again, if we have a positive operator, it's self-adjoint and it has this non-negative relationship on the inner product. That's what we're meaning when an operator is positive. We actually have seen some examples of positive operators. The proof of lemma 711 with T self-adjoint and alpha squared less than 4 beta that produces a positive operator, where the positive operator was this T squared plus alpha T plus beta I. That was a positive operator because that was greater than 0. In addition, any orthogonal projection, which we've talked about before, that's also a positive operator. So there are some examples of positive operators. Just like if we had a positive number, it makes sense to take the square root of that positive number. Now that we have positive operators, maybe it's okay to be talking about the square root of these positive operators. Let's now define what we mean by the square root of an operator. An operator S, a linear operator on a vector space V, is the square root of t, which is also a linear operator, if s squared is equal to t. That seems to be consistent with what we would think a square root would be. We use it twice and we end up with the original operator. Now let's look at some equivalences between these notions of positive operators and square roots, etc. This is now Theorem 727. Suppose we are given a linear operator. Pardon? What we're going to do in this theorem is show a lot of equivalences between different operators. So now in Theorem 727, we're going to start with a linear operator t. And now, if we can show one of these, then it's equivalent to all the others. Or if we have this operator satisfying one of these 5 statements, then it's equivalent to all the other statements in this list of 5 statements. So given a linear operator t, the following statements are equivalent. T is positive. And we know now what that means. We know that that means that T is self-adjoint and it satisfies this inner product non-negativity relationship. If our linear operator is positive, that's equivalent to saying T is self-adjoint. Duh, that was in part of the definition, but let's just say that. T is self-adjoint, and here's maybe more information. All eigenvalues of that linear operator are non-negative. So that's nice, because now if we have a positive operator, really what that means is we could think of it as having the eigenvalues of that linear operator are now all non-negative. Another statement that's equivalent to those first two is that T has A, so it has a unique positive square root. Just like if we took the square root of 4, that's either plus 2 or minus 2, we're now saying, oh, it has a positive, so it has plus 2 as one of its, as a square root. Yes?
The square root of the positive operator remains.
So now what we're saying is that if t is positive, then its square root, we could have many different square roots for that linear operator. We're saying it has one that's unique, that's also positive. So I'll give some examples in a minute, but we're saying that if we have a linear operator that's positive, then that linear operator, we can find a unique positive square root of that linear operator, of that positive operator. But we could find multiple operators that are square roots, but they may not be positive.
Another question is this theorem holds for any kind of product space?
So now we're not, well, we haven't defined anything relative, or we haven't restricted this, so the question was, does this hold for any inner product space? So we haven't what do I want to say, restricted this to being either complex or real. So right now we're just saying it's on some vector space V, real or complex. So this is now a linear operator on a vector space V. We didn't say real or complex. If that linear operator is positive, then it's also these next two statements. It's equivalent to those. Or the fourth statement is that T has a unique self-adjoint square root so it has even more structure, and E there exists an operator S on that same linear operator S on that same vector space V such that this linear operator can be factored into the adjoint of S times S, or composed of those two operations. Now, before we get into proving that, let's just get some examples. Show some examples of what we mean by matrices and square roots of matrices, just so that we're starting to get maybe a feel for or develop some intuition of these concepts. Examples with matrices. First example, let me call it T sub 1. Suppose I had that matrix, 1, 0, 0, 1, or I'm sorry, 1, 0, 0, 0. Can you cook up a matrix that when multiplied by itself will give you T sub 1? That really isn't too hard to do, is it? Since that's a 1 sitting there in the 1, 1 entry, I can now multiply S1 times itself, S1 times S1, and I get back T sub 1. So S1 is a valid square root for T1. Or S1 hat is minus 1, 0, 0, 0. That will also give me T1. S1 hat times S1 hat. In the textbook, page 145, suppose we now had T sub 2 that is mostly all zeros. What are the eigenvalues of T sub 2? They're all 0, aren't they? You have 3 0 eigenvalues. S sub 2. So now we want to have S sub 2 times itself giving us this 1 in the 1, 3 entry of a 3 by 3 matrix. Well, I can get the bottom row pretty easy. So now if I multiplied S sub 2 times S sub 2, I definitely get the bottom row in T sub 2. Now if that's S sub 2, I could still get the second row to be all 0 by just copying or bringing in the third row of S sub 2. So if I multiplied S sub 2 times itself, do you see that I get T sub 2's bottom two rows? And if I want to pull that middle row up to the top row, when multiplying by S sub 2, I can do that by saying, oh, just pull off the second row in S sub 2, and I will actually get T sub 2. So this S sub 2 is a square root of T sub 2. Let's look at maybe this one's really hard. Square root of the identity matrix is the identity matrix. What about T sub 4 being a diagonal with 2 and 3 on the diagonal? Well, now diagonals are like scalar problems. What's the square root of 2? Well, that could either be this square root of 2, but it could be either of those, right? And likewise for 3. Now, you should be able to, by inspection, find this square root. S sub 5 is minus 1, 1, 2, minus 3. That should have just popped into your head immediately. Maybe not, but if you multiply S5 times itself, you will obtain T sub 5. Let's look at another one. T sub 6. 3 minus 4 minus 8, 11. Does that look familiar? That's the same as T sub 5, isn't it? But we could also find an S sub 6 that's different from S sub 5, where now S sub 6 is 1 minus 1 minus 2, 3. I don't know what happened to my 8 in T sub 6. I guess it got tired. Half of it got cut off. Now it'll probably be duplicated. But let's now look at the eigenvalues of S sub 5 and S sub 6. If we computed the eigenvalues of S5, they would be minus 0.2679 and minus 3.732. So by definition of, or by using one of the statements in this theorem, is S sub 5 a positive operator? Look at statement B. First, is S5 self-adjoint? It's not even self-adjoint, is it? But its eigenvalues are negative, so that immediately kicks it out. What about the eigenvalues of S sub 6? those are at least non-zero. Or I'm sorry, those are positive. But S sub 6 is still not self-adjoint, is it? It doesn't equal its transpose. Let's now look at what we mean by matrices that, whoa, oh, I was having so much fun. So, we will pick up with showing or demonstrating some matrices that are actually positive and what that means relative to maybe these expressions that you might be used to in terms of polynomials. So we'll pick up with positive matrices, some examples, and continue with positive operators and isometries.